part 1 video for 5-2 properties of exponents and radicals. So this furthers our study that we started in 5-1, looking at the fractional exponents and going through and simplifying them. We're going to be doing a big variety of techniques today to simplify. So our essential question, how can properties of exponents and radicals be used to rewrite radical expressions? This is in your textbook on page 247. I highly suggest that you copy this down so that you have these 5 different properties that we will be using throughout this section. If you want to take a moment and pause, you can copy them from this video. They are not listed in the PDF of the notes, so it is something you will need to copy down. We have product of powers. That's where if you have the same base, you can add exponents, whether they're fraction exponents or not. Quotient of powers is where you can subtract exponents if you are dividing two things that have the same base. Power of powers, where you can distribute powers. We actually used that back in 5-1. Power of a product, that's where if you have a product in parentheses and the whole thing is raised to an exponent, you can distribute through that set of parentheses. And then negative exponent, if you have a negative exponent, that really means reciprocal. So here's our first example. It says, how can you rewrite each expression using the properties of exponents? So for part A, I have 81 there, and the base is the same, which means I am able to add my exponents together. So this is the same thing as 81 to the 5/6 plus negative 1/3 power. Well, we need a common denominator in order to combine those. Your common denominator is 6. 1/3 is going to become 2/6. So this is 81 to the 3/6 power, which is 81, excuse me for inverting that. 81 to the 1/2 power, and if you recall, 1/2 means square root. So the square root of 81 is 9. So that complicated looking problem in the beginning is really the same thing as 9. Part B, I have a quotient, so I am going to simplify before I deal with distributing that 2/3 power. So for my x, I have an x to the first in the top and an x to the 1/2 in the bottom. So that's going to be x to the 1 minus 1/2 power. The y only has the one term, so that's going to stay y to the 3rd. Well, 1 minus 1/2 is 1/2. And then I can distribute my 2/3. I am going to do some simplifying here in my head. I'm not going to write everything down like I did in part A. So x to the 1/2 times 2/3 power is going to be x to the 1/3 power. Y to the 3rd times 2/3 is going to be y squared. You can leave your answer in this format, or we can rewrite this as y squared times the cube root of x. Either of those would be correct for this question. So that brings us to example 2. It says, how can you rewrite the cube root of 16x to the 5th using properties of exponents? So we're going to go through and break these apart to find cube factors and basically rewrite it similar to how we did whenever we were breaking down square roots. The greatest perfect cube factor of 16 is 8, because I can take the cube root of 8. 8 times 2 is 16, so as long as I can remultiply and get what I started with, I'm good to go. X to the 5th, the greatest cube factor of that is x to the 3rd. And remember, when we multiply, we add exponents. So if we're dividing, we subtract exponents. So if I have x to the 3rd, I started with x to the 5th. My other radical has to have an x squared. So my first radical is all perfect cubes. My second radical is what's left over. The cube root of 8 is 2. The cube root of 8, or x cubed, is x, and then I would carry down the cube root of 2x squared. and that would be my solution. There is a shortcut to this as far as simplifying goes, especially for, maybe not necessarily for numbers, because the numbers you still have to think about with the square, like the square roots. But if you have variables, like let's say we're taking the 5th root of x to the 27th power. So I'm just making this up so you can see how this works. Instead of having to rewrite it the way that I did here, there is a shortcut to think about this. You want to think about how many times the index goes into the exponent of what's on the inside. So how many times does 5 go into 27? Well, 5 goes into 27 5 times. That gives you 25. The leftover amount, 27 minus 25, is 2. And that's how you would simplify that type of question. See how many times the index goes into whatever's on the inside, and then whatever the remainder is what the exponent still has on the inside. So here's your product and quotient property of radicals. This is what we were using. It directly ties into the power of a product rule, power of a quotient rule. And you can see here, if you have a radical of a product, you can split that apart. If you have the radical of a quotient, you can also split that apart. So that brings us to example 3. This does have a part A, B, and C. I'll scroll down so you can see C here in a moment. So part A, what is the 5th root of 16 times the 5th root of 8 in reduced radical form? So because those are both to the 5th, or taking a 5th root, and 16 doesn't have any 5th roots, neither does 8, I can actually combine those. I can multiply those together, and maybe the result would then have a 5th root. 16 times 8 is 128. And 128 does have a perfect 5th factor. And that perfect 5th factor is 32. Because I can take the 5th root of 32. 32 times 4 gives me 128. So 4 would go in the second radical. 5th root of 32 is 2, so that 2 is going to come out. I can't take the 5th root of the 4, so that would have to stay in. Part B is a little bit different because I do not have the same number in my radical. The first one is a 6th root, the second one is a 3rd root, so I need to think about these as fractional exponents so that maybe I can get the same fraction and I can go through then and combine them together. So this is going to turn into 8x to the 1/6 power. This is going to be 2x to the 1/3 power. Well, we can't make the 6 into a 3, but I can turn the 3 into a 6. One-third can become 2/6. I can then distribute the 2 into that 2x term. So I can think about this as 8x to the 1/6 power times 2x, the quantity squared, is going to be 4x squared to the 1/6 power. Then I can pull the 1/6 power out. So just like I could distribute it, I can undistribute it. I can factor it out. So that's going to make it 8x times 4x squared, the entire thing to the 1/6 power. Now I can multiply what's inside together. And that's going to give me 32x to the 3rd to the 1/6 power. You can leave your answer like that. You can rewrite it as a radical if you wanted to. There's really no point in simplifying that really any further. You could make it x to the 1/2 power, 36 to the, or 32 to the, 32 is 2 to the 5th, so 2 to the 5/6 power. There's really not much else you can do with that. That's pretty much as good as it's going to get. And then we have part C. Well, according to my rule, if I'm taking the radical of a fraction, I can take the radical of the top over the radical of the bottom. It is not proper to have a radical in your denominator in your final answer. So I need to multiply by something to make it a perfect cube in the bottom so that I can actually take the cube root and make it disappear. Whatever I multiply by in the bottom, I have to multiply by in the top. So we want to think about what we can multiply by to turn the number into a perfect cube and to turn the variable into a perfect cube. Well, the number that I have is 9. I want to see what I can multiply by 9, the smallest number I can multiply 9 by, to get something I can take the cube root of. Well, I know I can take the cube root of 27, and if I multiply 9 by 3, that would give me a 27. So 3 is one of the numbers I have to multiply by. For variables, when you multiply, you're really adding on to the exponent. So you need to figure what you need to add on to the exponent to make it something that's divisible by 3. Anytime it's divisible by the index, it's going to be either a perfect cube or a perfect fourth or perfect whatever your index is. So the m currently has an exponent of 1. I need to add 2 more onto that. So I'm going to multiply by an m squared. By multiplying the same thing on the top and the bottom, you're multiplying by 1. And remember, just like we talked about before, when you multiply by 1, you're not changing the value of your fraction. So on the top, I'm going to have 6 m squared n, I multiply the big 2 and the big 3 together, over the cube root of 27 m to the third. Then I can actually take the cube root of the bottom. The cube root of the 27 is a 3. Notice how it comes out of the radical. The cube root of m to the third power is an m to the first power. No absolute values necessary because I was dealing with a cube root. This is where we're going to conclude the first video for this section. I'm going to pick up with example 4 in video 2. So please go back, rewatch this video, go through anything that you're not sure of, and reach out if you have any questions.